Thank you very much. It's my pleasure to introduce Mr. Brian Gahan.
Thank you very much. It's a pleasure to be here, and appreciate being invited to provide a little bit more of a technical perspective. I believe you all have been talking more on the policy issues, economic issues related to petroleum, oil and gas, and I was asked to provide a little bit more of a technical side of it. It's a very broad area to just say, hey, can you come up and tell us about how oil and gas works from a technical perspective. So forgive me if the slides are a little bit, and you probably are saying, please don't make them too technical, and they're not. But what I'd like to do, if I can get, are the slides ready to go here? First slide? I think I'm good once we get that up there. Fantastic. Thank you. So I titled my talk, Advanced Technology Development for Oil and Gas, and I'm going to touch on a few things here. I may have to have a little help after all. If you could just check that connection to that USB. Just make sure that's in there. Worked fine before. Yeah, go ahead. Okay, just to give you a quick outline here, and we'll probably have to race through a couple of these things. I know you want to keep this on time. But I'll provide you with a little bit of background, a little bit of history, just briefly let you know kind of a historical sense of where this business has come from. Location of resources in general, you may have seen some slides on this from other speakers. Steps to recovering hydrocarbon, a little bit on the supply scenario. Touching on unconventional resources, a few technology examples, and then I'll talk a little bit about some of the work that I'm doing with laser applications as an example of high-tech applications being pursued today. Just as a background, petroleum really means rock oil, and it's been around forever. It's a natural occurrence. It's from a pre-colonial times. Oil can be found in natural seep springs and pits, American Indian, Native American, found and used, found different reasons for using it as paint or medicine. Once the country started moving a little bit further west in the colonial era, get into Pennsylvania, Ohio, the Appalachian Basin, and they started collecting the natural seep oils and using them for also medicine and different things. But what they did was they had to, for preserving the food, for preserving meat, they needed salt, and they would drill for brine wells. What they inadvertently did was they drilled for oil. They considered it to be a contamination. It was a byproduct. And in fact, they actually had to shut down some of their brine wells because they were contaminated with oil. They had gravitational separation of the oil from the brine, and then they used that for many different things. I just put a couple things up here: medicine, fuel, lubrication of machinery and axles. They actually mixed flour with oil to make a grease, caulking, waterproofing. And then moving into more of a modern era, direct drilling for oil from 1859 to today, starting with a cable tool method where they're actually taking a steel bit and just actually moving it up and down on the rock and just chipping and pounding at it, to where they actually went to a rotary method, which is still used today. And of course, the uses for oil are quite vast, and we're very dependent not only for transportation and other energy uses, but from the feedstock, the petrochemicals, plastics, fertilizers. So we're very much in touch with these. This is a gentleman, I don't know if you'd lend him money, but somebody did. This guy's name is Colonel Edwin Drake. And he got the bright idea of drilling for oil, specifically for oil. At that time, there was the beginnings of a market. Whale oil was starting to decline. They weren't being able to kill as many whales for kerosene and light for lighting lamps. So there were other technical advancements which were discovered, which allowed to refine some crude oil into kerosene and other lighter fuels, lighter ends, and using that as a substitute for whale oil. So here you have the economics part of it playing into the technology and finding a different use and an economy for oil rather than being a byproduct. So he got 20 barrels, $20 a barrel, and he pumped 20 barrels a day from this little rig here. He struck oil at 69.5 feet, which turned out to be one of the shallowest discoveries of oil ever in the world. Just happened to find the right place. Next, please. And soon afterwards, you heard of the gold rushes and the 49ers in California. Well, the same thing happened with oil. As far as you can see, they're putting up all these wooden derricks and cutting down all the trees to build the derricks, and you had a sloppy mess. That continued on until really the next biggest thing happened was what is considered to be the birth of the modern industry, was spindle top. And you see the gusher here, and Hollywood's played up this whole idea of gushers, and you hit a gusher and you're rich. But it actually was something they didn't want to do. They didn't know how to handle it, because you ended up with a lake of oil that you had to end up picking up and putting in actual barrels. But this was the world's first gusher, America's first gusher, January 10, 1901. It was not only the first gusher, but it was the first use of rotary drilling techniques, which is what we still use today. And is also the first use of a drilling mud to try to control pressures. That obviously didn't work well here, but next slide. From that technology at that time, you can see here's some examples of different drilling rigs, onshore and offshore, and drilling ships and tethered platforms that are being used today. So you can see the technology has advanced incredibly since 1901 to the point where we're deep out in the oceans and we're finding oil in places that were never even conceived of before. Just to give an example, as we step out into the ocean, we have the fixed platforms, which have been around since probably World War II vintage. And then as demand and technology allowed, continued to move out and engineered some pretty complex systems into subsea and spar platforms. Next. And again, just to give you an idea of the technology changes, this is, circa 1800s. The main mode of transportation for moving oil was actually in barrels. You can see barrels on the barges, and they move them up down the river. Before that, they just poured the oil right into the river, and they dam it up further downstream, so just siphon it off when they needed it. But the next slide shows you we're a little bit more advanced today. We're a little bit more concerned about our environment and getting really as much money from the investment as possible. You don't want to waste it. You want to save it and take it to market. And so here you have probably a double-hulled tanker. Next. I just want to mention, there's a lot of information out there about the history of the oil and gas industry. And there's a guy by the name of Daniel Yergin. Many of you may know his name. He's the author of this book and a video series called The Prize. And I would recommend it if anybody is interested to know a little bit more in detail about Rockefeller and all the other interesting people in the industry, throughout the industry, and the advancements of technology. So it's a good place to get good single source to get good history. Now the question is, where do you find petroleum in the world? Well, I found a couple of maps, and one of the things that is noticeable is that here's the continents, and there's a lot of oil and gas structures along the fault lines. That's an interesting observation. Next slide. And then this is trying to take into consideration size and location by some balloons here as to where some of the major oils finds have been in the world. You can see they're pretty well scattered. It's just not the Middle East. It's just not the United States. But it's pretty well all over the world, with the exception of, say, Greenland, Antarctica, of course. Nobody is allowed to drill down there. But there's a sizable amount of oil pretty well distributed. Different kind of rock. Okay, we're drilling down into the earth. We're drilling miles into the earth, and where are we drilling into? And we're drilling into igneous, sedimentary, and metamorphic rock. And for most people, they pick up a rock. It's a rock. But from oil and gas standpoint, they are pretty significant. Igneous is a rock like a granite or basalt. It comes directly from a volcano. It's cooled. It's crystalline. It doesn't have any ability to transmit fluids. Sedimentary is when you have erosion. You start getting bits and pieces and chunks and sand grains that are knocked off the igneous rocks, and they end up forming in sediments like riverbeds, over time, and pressure and temperature starts to push those together. They cement together and form things like sandstone, shale, and limestone. And metamorphic is just putting those under pressure. But slide. Well, what we're interested from an oil and gas standpoint, as far as reservoirs, where oil and gas is located, is in the sedimentary rocks. And just to give you an idea, a lot of people think, and I come across this a lot of times with people who don't have any experience or knowledge about the petroleum industry, is they believe there are actual lakes of oil and gas under the ground. Well, there are, but not quite. What you've got, Beck, this is just a rough geometric representation of how round grains will form into a rock to show you the differences in how much pore volume you can have in the same volume of rock. If they're lined up as they are on the left side, you get about 26% of the volume is pore volume that can hold a fluid. But if they line up like they do in the middle, you get almost 50% of that can be fluid. Or if they're lined up on the right side, you can get even more than that. So they're not open lakes, but there are large volumes of fluids underground. And of course, how do they accumulate? There's different kinds of traps. I won't go into it, but you can see that there's different structures underground that will cause the oil and water to separate gravitationally and be captured under an impervious or impermeable cap rock. This was an interesting slide. I really hadn't found it until I started to put this together, but this is showing the age of the rocks. This is a geologic time scale starting from a current period at the top all the way down to Precambrian, 570 million years before present. And they did a little correlation here and found that there's actually only 6 intervals, time intervals, that have generated almost all of the world's oil and gas. So that was interesting to me. And then this is just a slide to show you that there's certain steps that go into the whole process here. You've got assessing your resources, exploration technologies, drilling, completion, and stimulation. Once you do that, you've got to produce it. So there's production technologies, then you've got storage issues, and then listed on here is methane hydrates, which is a whole different animal I'll just briefly touch on. From an exploration standpoint, it's just not you go out to take a well or a drill with you and drill a well. You have to know where to go. And what you want to do is you're exploring for it. And there's really 3 phases. There's wildcatting, which is just going out where you really don't know, but you have a pretty good guess, where there's never been any drilling before. There's an expansion where you have established a location where you've found mineral. And then there's a fill-in where you've outlined your field and you start infilling and putting more wells in there. Detection methods can be direct detection, like a seismic method, like the truck on the top actually has a thumping mechanism which thumps on the ground, and it has recorders behind it. So you get, if you can hit the slide, this is kind of the same thing but in the water, but you have a seismic source that sends sound through the rock and it bounces back and collects on the hydrophones. And in this way, they can determine, and you can see below, that's a 4 or 3D seismic interpretation of what they've done by thumping the ground. And people actually know how to read this. I'm not one of them, but that tells them where there's likelihoods of accumulations of oil and gas based upon the structural elements underground. There's also subsurface mapping, conceptual modeling, and remote sensing, among others. Those are major ones. And if you hit it one more time, one of the other things is kind of a virtual thing, or 3D, where you're actually putting glasses on in front of a computer. And I know UIC has a virtual lab, and I don't know if they get into the oil and gas side, but it's pretty interesting. A room where you put the glasses on and everything seems to be right in front of you and you're grabbing it. Okay. This is another method of trying to find new sources of oil and gas where older wells have been drilled and they've been run through the process, and they've actually missed different layers and lenses of oil and gas. And there's methods by which engineers will go back, and geologists, geophysicists will go back and try to find this. And this is one method that we were involved with at my old company, Gas Research Institute, of crosswell seismic imaging, where we actually had 2 existing wells. In one well, you put the source, and the other you put the receiver, and then you could determine, cross one well to the other, what was in between and if there was anything that you missed. And this is just kind of giving you an idea of how quickly things are, a little bit of a sense of drilling technology. The old method of what they call spring pole, and that goes back to the Chinese, 2000 BC, or about 4,000 years ago, where you stuck a springy pole up there, and you had a hard metal or some other capability of cutting the rock, and you just bounced it up and down. And they actually drilled and completed wells with that method. Then they, zooming up into around the 1800s, middle 1800s, when the industrial era, they started putting steam on the rigs. And then you get into 1900, again, the spindle top, you get the rotary rig methods. And then the 2000 and beyond is some of the work that I'm working on using lasers to cut rock. So I'll talk a little bit about that too. From a drilling completion standpoint, I'm being very simplistic here, believe me. But your main components are, you've got a derrick, you need power at your well site, so you can turn in a rotating fashion the pipe and the bit that's at the bottom. You've got mud and fluids which circulate and keep control of the pressures and lubricate the bit. You've got casing and tubing that go down the hole, steel casing and tubing, and they play a role in making sure that the fluids go where you want them to go, whether they're fluids you put in or fluids you take out. There's logging and coring technologies to try to understand geologically where you are. Cementing is when you're getting finished, you've reached where you want to go and you want to put your pipe in place permanently. You can run cement down the inside of the well and it comes down to the bottom and comes up the outside of it, cements it in place. And then perforating is when, after you've got it all cemented in place, you want to reconnect with the reservoir and allow the fluid to enter the well. Other ways of looking at drilling technologies, again, very simplistic, but you've got offshore versus onshore, two completely different environments, require different types of engineering issues to be addressed. You saw some of the offshore types of platforms that have to be designed and built. Slim hole and micro hole, where you're trying to do more with a narrower diameter of a pipe, in getting into coil tubing type drilling, where you actually have a reel of a narrower diameter and a pipe or a drilling string. Deviated and horizontal wells are a big thing too, because you can, instead of going vertical, you can actually kick off and go in different directions depending on where you think the oil and gas is. Reservoir specific issues having to do with what kind of rock are you getting your minerals from, your oil and gas. Coal is an example. That's been a big factor in replacing our reserves over the past 10 years. Fluid chemistries, again, drilling muds, those types of things. You really need a chemical engineer to figure out what kind of additives you want to put in your mud to make it either heavy or lubricated, whether you want water or oil or other synthetic types of additives. So it gets kind of complex on the chemistry side. Casing and tubulars, the different types of materials that you use. If you have corrosive activity, you want to use something more of a stainless steel, which is quite expensive, or a titanium. And then the computer technology itself has allowed us to do so much more in recent years than we have in the past. So this kind of question, I'm sure, has been raised before. Is there enough natural gas to meet the demand? And my experience has been is that there's always been someone that comes out and says, oh, we've got about 8 years, we got 12 years or 10 years of reserves left. Well, that's proven reserves. That's what they found or what they think they can find. And that was the same type of scenario since the beginning of the oil and gas industry. In the 1930s, they say, oh, we got about 12 years of reserves. Obviously, more than 12 years of the industry since then. But it's just a standard issue of, do we have enough? And that's always debatable. One of the interesting charts that I've come across is kind of this energy substitution concept. What you have on the left-hand side is the percentage of all the energy. So from theoretically, it's 0 to 100. And then on the bottom, you have the years 1850 out to 2050. And what this graph is showing is the different major types of fuels that have been used over time and how they fit in the energy mix. And you can see that, let me get my pointer here, Wood, solid fuels, wood and coal, but wood particularly here, moving to coal. Wood was a primary fuel used in the 1850s or just right after. Steep decline down. It came out of favor when we found coal. And so we started using coal, and that started to fall out of favor because we found oil. Oil was more fungible, and it could be better address the needs of our transportation system, so that's starting to go up, and people think, well, okay, we're at a peak now. And of course, natural gas is somewhat of a byproduct or a co-product of oil, and that's running a curve as well. And then you've got nuclear here, and I think this is representing solar or other technologies. But you can see that as time goes on, there is substitution based upon what the economics and the environment dictate, and the expectation is that the gaseous fuels will continue to go forward. Nuclear is limited by a supply of uranium, but the expectation is that natural gas will lead to, which is a low carbon, to a no carbon, which is hydrogen. So that's where the hydrogen economy theories come from. And this is another curve you probably heard about. This that should be a period there, but M. King Hubbert, he came up with this concept in around 1970 that he observed that most of the production in the United States peaked in the 30s as far as the big fields. And that was not including, of course, the Gulf of Mexico. But so he theorized that, you know, the production from those wells was going to peak as well. And he predicted that 1970 was going to be the peak. You can get into all kinds of debate on this issue, and they've got schools and classes and all kinds of different things talking about this. But the whole idea is that at some point there's a limited resource. It's pretty well acknowledged it's limited. The question is, where does that peak take place? But that's just a point that I think you should be aware of, that we are either at or near this peak, according to most experts. From a resource base, how big of a resource do we have? North America, this is just the gas side, about 2,000 trillion cubic feet of reserves. And it's a large reserve, and it's very diverse. Just looking at some trends here, we're talking about production history. We've got a maturing base, and you can see the decline from 1990s to 2000 of lower 48, which is the blue, and the Western Canadian gas, which is the green. So we are experiencing some maturing resource base. The other thing is this is billion cubic feet a day and numbers of gas rigs that are drilling for natural gas. This is gas production and number of rigs. What it's showing is that we're putting more rigs at the problem, but we're not getting really that much more gas as a result. So the return is starting to decline as well. Okay, just another trend. This one didn't come out at all, so I apologize for that. But this is just, again, showing total footage drilled, which is this light line here, and just below it is the petroleum wells completed. So, again, it's following the same type of idea. And the average well depth and cost. Average well depth, this is kind of interesting. The depth is increasing, and so is the average cost per foot, quite a bit, too. So it's actually exceeding. This is just in the 90s. It's actually exceeding or crossing over that line. But again, trend, just something to be aware of. These are things that factor into where we are today. Gas production versus gas production capacity. Our production capacity and the production. So we're producing just about at our capacity right now. Next. These are kind of potential price ranges. This is $2002. Again, it can go up and down depending upon, you know, supply demand. So that's basically the cone of the expectation of prices. Now, that's annual average prices. There are peaks above $8, but future supplies, lower 48, Gulf of Mexico, Rockies. So it does take a mix, and then some of these slides I saw earlier, it does take a mix of different sources and different locations of gas, and you can see the LNG portion of it's increasing. Alaska is increasing somewhat, but it takes all of them to really meet the demand. This was something that researchers like to see? What's the impact of research on what could happen in the future? And this little orange section at the top is a component that is best guesstimate is a direct result of new technology. So what this slide is saying is if you don't have continuing research and development in developing new technologies to address more difficult conditions of finding and producing your petroleum products, you're going to have that decline that you're seeing, the natural decline that we're seeing because we're at capacities and we're reaching those peaks. So we're squeezing more out with more technology. You can pass this up. Unconventional gas growth. Again, conventional is pretty much what we've been traditional oil and gas wells. Non-conventional is things like coal bed methane, oil and gas shale type rocks. More difficult, require different types and new technologies to drill, but they are becoming a larger and larger piece of our pie. Go ahead. This is just some coal bed methane resources. Now, coal bed methane is something that's relatively new, something that Gas Research Institute was very involved with, and probably DOE, but I don't know to what degree percentage-wise, but they were both involved in coming up with new technologies to develop this resource. It's a vast resource of 703 trillion cubic feet. But there was just really no understanding of how to get that resource out of the ground effectively. There was probably about 10 years worth of research, and now a good percentage of reserves can be attributed to, that are replacing reserves today, can be attributed to coal bed methane. You can see that there's quite a bit of coal deposits that are capable of providing natural gas from coal seams. And just to show you again how much it's ramped up, if this goes from 1983 to 2003, how much gas has been produced. This is just coal bed methane gas, and these are just different basins that they came from, but it's significant, and it's where technology really did step up to the plate and hit one out of the park. There's another source that's theorized that we could go into, deeper gas structures. Estimates are 7% of gas production in 90, or that's actual 99, but 14% in 2010. So you got to go deeper. It's not at the surface anymore. It's not easy rock to get into. Next. This is methane hydrates. It looks like ice. It burns. Got a flame on it. Next. And because of the structure of this, with pressure and temperature, the crystals contain natural gas up to 170 times their volume. So it's very prolific. The question is, how do you get at it? It's very difficult. It's not stable. Next. But worldwide, there's quite a bit of resource. A lot of oceanic, continental resources estimated from oceanic 50 million trillion cubic feet, continental 12 million trillion cubic feet. Our conventional gas resource is 13,000 cubic feet. So you can see just relative how big this is. It's a significant amount of gas. Again, how do we get it? It's difficult technology-wise to get to it. If 1% of hydrates are recoverable, that's 3,200 trillion cubic feet. That's a pretty good dent in what we're producing, or what our resource base is now based on conventional. Conventional natural gas technology recoverable resource, 1,300 trillion cubic feet. So, again, conventionally available. A couple of the issues related to why is it difficult. You've got production problems, safety problems, resource characterization. So when you start producing it, it starts to dissociate, and then you get bubbles. Say if it's subsurface in the sea, you get bubbles that come up that expand rapidly. How do you capture these before you cause problem to your production platform or ship that you're drilling in? Seafloor stability. Are you going to have sloughing off your seafloor? It's going to cause instability. And then questions about global climate change, too, if you're releasing these things into the atmosphere from the ocean. Go ahead. Distribution. There's quite a bit of distribution here in the U.S. From Atlantic, Gulf of Mexico, Alaska, and Pacific Ocean. Talking 320,000 trillion cubic feet. Next. Drilling, completion, and stimulation objectives. Stimulation is when you go into a well after you complete it, get it ready to produce, and do something like hydraulically fracture, acidize to try to improve the channels that allow the gas or oil to flow to the well. But we're looking for faster, deeper, cheaper, and cleaner technologies. We're dealing with high temperature and pressures, higher temperatures and pressures than we've dealt with before as we go deeper. We have to start using smarter drilling systems that rely on computers and predictability type logarithms. We're looking at harder rocks to penetrate. We're also trying to reduce the cost at the same time. We've got this challenge of trying to drill in more difficult environments, but doing it as cheaply and as efficiently as possible. And of course, we got to be clean about it. You know, there's somebody always watching the back in the oil and gas industry, waiting for something to happen so they can point a finger and say, "Look, it's not safe, it's not clean." But for the most part, it's done very well, done very environmentally friendly. Advanced drilling technologies. There's just a short list of things that have been developed or are in the process of being developed that are pushing the envelope in the drilling arena. High-pressured coil tubings, microwave processing of cutters for bits, which is TSP, horizontal well technologies, underbalanced drilling technologies. So this is just a really short list of different things that are being addressed just in the drilling arena. Gas storage also has a lot of issues too. Just because you produce the gas, now what do you do with it? You got to put it somewhere, but you got to be able to get it out when you want it. Okay, so if you turn on your furnace, you want gas coming to that in the wintertime. They don't drill the well and pump the well right to your house. They have to collect it. And the problem with these storage concepts, a lot of them are underground in existing abandoned reservoirs or salt mines. And the question is, every year there's a loss in deliverability because of contamination or other issues, precipitates, that reduce the ability for that reservoir to give you as much gas as you want to get based on the previous year's deliverability. So there's different kinds of concepts and technologies that are being looked at as far as how, where, and how best to store natural gas. This is an interesting little, there we go, cement pulsation. This is an example of a technology that someone has been working on. One of the problems that comes in is when you cement a well, you put the cement down the hole, comes up the other side, you put just enough in there so that you have an empty space in the middle, and you're cemented in place. But the problem is, as it sets, you can get gas bubbles coming in from your gas zone, and it can destabilize your cementing, and so you don't get a good cement job. One of the things someone came up was, well, what if you vibrate it by putting sound waves down the column of the wet cement as it's gelling? And so it actually works. It's just one technique that tries to give us a better well. It's reduced costs. It costs very little to do that, but it's just people using their minds trying to figure out better ways to solve some of these problems that are everyday production problems. Ultimately will lead to more production out of that well, and certainly less cost. This is just this is a microseismic mapping. We can skip this. Another big technology is hydraulic fracturing. If you've got a hard to produce rock, something that's not very permeable. Permeable means the ability for the rock, for fluid to flow through the rock. If it's not permeable, what you have to do is you have to crack it with a lot of hydraulic pressure. You put pressure down the well to the point where the rock actually cracks or breaks. This is kind of how we think of it as an engineer. You get it come down, you get this nice wing coming out, breaking in the rock. But actually, this is kind of how it happens, and you don't get as much length on it. You've got different places where it's breaking. It's breaking above and below where you want it to, so it gets kind of dirty. But there's technologies that have been developed and are continuing to be developed to try to address this issue. CO2 capture and storage, again, the sequestration issue. You get emissions from plants, and you want to try to find methods or ways to to sequester them, and one method is under the ground. There's methane hydrates, aquifers, depleted fields, and coal seams that have been proposed, and these are things that are being looked at. And then from a geophysical side, there's, again, looks the same to me, but someone says that looks different. And but the people that are doing this are saying, hey, I can tell more clearly in this picture where I want to drill versus in this picture. And that's just technology at work. Let's see if I got how much time. Okay. This is a project that I've been working on for about the past 7 years in different venues. But the concept here was originally through GRI, Gas Research Institute, trying to find technologies, techniques that would allow drilling to be, again, faster, better, cheaper. And one of the things that came through as a proposal was, how about using high-power lasers? At the time, the federal government was trying to find uses for the old Star Wars lasers that were from the Reagan era that were developed in the Army and the Air Force. So we said, that sounds interesting. Let's take a look at it and see what they can do. Okay. Next. That obviously didn't come out. It's not important. Go there. There we go. There's different things that we theorize that a laser might be able to do downhole. You've got the actual drilling process. Perforating, which this schematic is showing a perforating going down the well, piercing through the steel and the cement and the rock to create a channel so that the fluids can go into the well and up and out. Casing cutting and abandonment, so cutting metals downhole, cutting windows for multilaterals, cutting a hole in the pipe so you can deviate a drill bit through and go in a different direction. So there's a number of different things that could be done with this technology. This is a laser that I'm using right now. This is a 5 kilowatt laser. This is the latest technology. It's called a fiber laser. And it is quite an interesting little instrument. There's nothing like it that I've ever seen in the laser world. We used lasers at Argonne, which were older. But even the newer commercial lasers can't really match this. And as a result, this laser is replacing and probably will replace almost all of the current commercial systems that are out there for automobile manufacturing things. But it's relatively compact. It's smaller than a refrigerator. It's not that heavy. You can run it off a laptop, and it's like a point-and-shoot system. So this is something you can stick in a vehicle and take to the well site. When we were doing the laser work, we originally started out again with the military lasers. We were using 6 kilowatt up to 1,600 kilowatts, which was the Army laser, the Miracle laser, at White Sands, and just trying to determine, number one, can a laser cut a rock? And we said, yep, it sure can, but it's not very efficient. You're wasting a lot of energy doing it. You're turning the rock into vapor. So next step was, let's look at the lower power industrial lasers that are commercially available. And we worked with Argonne on that. They had a couple different lasers here that we liked. They were smaller power, just about 2 kilowatts and 6 kilowatts. And said, how much energy really does it take to cut it? And we said, the answer is a lot less than what people thought. So let's keep going. So then we found out about this high power fiber laser, and we got a hold of one of those. And we said, can it, with its greater efficiencies and all the other benefits that it has as far as low maintenance and et cetera, how does it stand up? And it turns out that it stood up very well. It actually was an improvement over the other industrial lasers. But one of the things that has really got the eye of the industry, especially the service companies that go out and perform these services, perforating, is one of them. And one of the things I like about it is it's non-explosive technology. And you're getting away from taking explosives, putting them down the hole. The explosives are shaped charges like a bazooka. They'll penetrate through steel. And so it's a safety issue, it's a terrorism issue, it's all these different things that are negative to the company should something go wrong. So they want to find out, can this substitute for explosives? It's also real time. You set off an explosive charge and it's gone. You can't stop it. This is more of a real-time input-output scenario. You've got open solutions. You can aim it and point it in different directions. You've got potential to extend your perforation and simulate a hydraulic fracture, where we saw we didn't have really much control over if we just pump pressure down the hole. And the other is it improves the flow condition. We don't have any mass transfer from the molten steel and the combustion gases being shoved out into the hole that you make, so we're not damaging the hole, and therefore it's producing about 90% better than the conventional method with the explosives. This is something we observed and is important, is that in different kinds of rock, you get different kinds of reactions in how it actually cuts. With a carbonate like a limestone, it's just a chemical reaction. You got a CaCO3, it's a carbonate. You put heat on it, and it turns it to lime and CO2. Well, what is that? That's the same thing you do to make cement. There's really no upper tier level for the heat, so you just point it, fire it, and it makes a hole. Sandstone's a little different. You don't want to get above the melting point of the quartz and make glass, so you have to throttle a little bit. But what you do is you rapidly expand and contract the size of the grains, and they separate from each other, and they sand apart, and you make a hole. Shale, same thing, and steel it's a solid structure, and you just melt it. So the same laser, same wavelength, same power can cut all those different materials. These are just some examples of things we cut with it. We put the laser on there. We cut 12 inches into a piece of limestone. And then we took a 1 foot block of sandstone, which, believe it or not, was $1,000 for this block of sandstone. It's a specific quarry in Ohio that is used for laboratory experiments. But we gridded it off, measured it off with permeability. Next slide. And we cut through. It's not exactly straight because we went in from 2 different directions for purposes of the experiment, but it cut through, and it simulated what you would do down hole. Next slide. And then when we looked at the permeability, there was some improvement along that tunnel as far as permeability, which basically says we didn't hurt the rock. We didn't cause any reason for the fluids not to flow through there. Okay, next. Then when you look up real close at it, the grains are all in place. Nothing's melted. So we did better than the explosive charges. And the interesting thing about it is you're firing into the rock, which acts like an insulator. This is the actual picture from the video with an IR camera, infrared. Along that line is right here, and this is the hole. It's hot at the hole, but as soon as you get away from the hole, it's cool. So all the energy is being used to make the hole. This is even closer. We made some thin sections just to show, gee, what do those grains look like really up close? This is before it. Next slide. This is after. Well, after didn't show up, but this is, believe me, it's the same. And then this is the shape charge perf. You can see how it's kind of crunched, and all the channels for the fluid to flow are all blocked, and the matrix is crushed. So big difference. Then we said, well, how's it going to perform under pressure? So we came up with this little contraption that actually allowed us to shoot, allowed us to shoot a beam through a couple compartments and into the rock. And it was basically said, hey, no problem, actually likes the pressure. Here's the actual device that we used to simulate that. We had the pressure simulation such that you would find down holes. That was all simulated. Next. And then this is the actual targets we fired on. We didn't want the steel, which represents the pipe in the hole, to be all the way across because it gets hot and it rapidly distributes heat, and we'd be melting our pressure barriers on our instrument. So we used the insulating nature of the rock and just used a small piece, cemented it. So this is basically the same condition you would find down hole. You're going to penetrate through steel, through cement, into the rock. And we did. Berea sandstone and limestone. And this is just a CAT scan to show that we did. I don't know why my line's crooked. It should be straight, but this is the molten steel on the outside. It doesn't go inside, which is good. And for the time we had it on, it penetrated out to about this distance. This is the part where I say, gee, it's all great in the lab, but how's it going to perform out in the field? One of those things that we want to know as engineers, can we make this a practical application? So for this case, the Army actually put one in a Humvee, and they powered it off the diesel engine of the Humvee, so it was all self-contained. And what they used it for, next slide, was they fired the beam at unexploded ordnance. So there's a landmine out here. They lined it up, fired the beam at it, and exploded the unexploded landmine. So that was kind of testing the technology out. So that if you can put it in a Humvee and take it to Afghanistan and make it work, it's pretty rugged. Then another instance, this is the same type of setup here, laser conditioning equipment for the power. Plug it into their three-phase, use their water on site. This is a hospital in California, very hard, dense concrete due to earthquake codes. And the earthquake codes are once again updated. They need to thicken their wall. Well, how do they do that? Well, they got to use jackhammers. They got to use all kinds of equipment that's going to make a lot of noise, a lot of mess, and they're going to have to move patients out, and they don't want to do that. So some friends of mine at EWI said, hey, give us a shot. We'll try this laser out. We know it can do some pretty fun things. They used the beam as a pilot hole. So here's what they hooked up to the wall, shot the beam in. It did the whole carbonate to a line type of a dissociation. And then they went in with once it was the pilot hole was established, and they went in and they used a mechanical drilling bit to the right dimension, and they epoxied the rebar in, and they were ready to, once they did that with the whole wall, they could put up a new structure. Didn't have to move a single patient, and the loudest thing on there was the fan that was taking the debris out of here. So, again, another on-site example of a technology that works. But the basic thing that I want to get across here is that we've got to meet these future energy needs from oil and gas. Yeah, there's alternate energies and emerging resources and a number of different things that help meet our needs. But we still need oil and gas. We just can't turn it off. There's just no way. So we need technology advancement in order to do this. And you can remember from the one slide where I showed you the effect of technology on reserves. We definitely need to have that. It's getting more and more difficult to get more and more oil out of rock in more extreme conditions. The other thing is that we have unconventional resource development, coal bed methane, shales, oil gas shales, methane hydrates. All of these things need technology to be applied so that we can get as much out as we can. And then, of course, the energy, environment, and economics they all work together. And you really can't have one without the other. And I heard a little discussion this morning about, putting all this money in from the government, trying new different things, but it's just not taking. Well, and it was explained that, the economics weren't there. And that's very true. You have to have, in a free market condition, you have to have the economics in order for it to take. And by allowing the price of gas or gasoline and other fuels to go up and down in the free market, you're now encouraging these types of things to take place. You're encouraging these economics to force new energy decisions. So it's a good thing. May not be for you when you don't have enough in your wallet, but in the large scheme of things, it's a good thing. It creates substitution and diversification of your energy sources. And that's what I had. I hope that addressed what you all were looking for, Chris. 1 hour to do the whole technical on petroleum engineering is quite a task, but I'd be more than happy to answer any questions you have. I'm very happy to do that. Thank you.
I'd like to hear a little more about the methane hydrates. How were they formed, and what kind of technologies are we going to need? What kind of technological development in order to use them? It's sort of a new topic for me, so I'd like to get more of a feeling for it.
Okay. It is a relatively new topic, and the one country in the world that's been putting the most money into it is Japanese, because they have nothing indigenous as far as energy, other than they are surrounded by these huge pockets or deposits of methane hydrates. So they see that from a national perspective as priority one from their energy perspective. We're also blessed, and the world is blessed that these are relatively evenly distributed. And they're found in conditions where the pressures and temperatures are such that you have sort of a water cage and an ice structure and methane embedded in it. I'm not an expert on how that methane got there. There's different theories about abiogenic gas, or gas that actually is developed by the Earth. It was primordial, and it's continuing to come out of lower and lower levels. And then there's the biogenic theory that says, no, well, that has to come all from organic material from the past. So wherever that source is, I'm not quite sure, but certainly over the many eons, there's been a lot of turbulence, upheaval, plate tectonics, and so where it comes from, I'm not sure, but it's there, and because it's in a condition where there's water present and its pressures and temperatures are right, it does form naturally this cage, which allows a lot of this gas to be captured in that. Technically, what are you going to need? One of the things is you need to be able to either drill it or release it in situ in such a way that you can control the situation. With a regular conventional well, you have high pressures as you drill down, just because the rock, the overburden is so heavy, it weighs a lot, and it's going to push down on the rock structures below. So your pressures are higher at lower depths, and you need to control that in a conventional method by using fluids, like a mud fluid, so that your weight of your mud column is higher than the pressure that you're experiencing at that depth, and you balance that out. If your column's not heavy enough, then that gas comes out of solution and it comes out the well, and you have a big problem. Something similar has to be designed, I think, for the methane hydrates, but you don't have a fluid column specifically over top of it. Maybe something like that has to be designed. I don't know. The other thing about it is as you're dissociating, or you're removing the gas, you're dissociating the actual ice crystals that the gas is trapped in. So it's like you're digging in a sand pile, and it starts to all fall apart. And again, not sure how that's all going to be done, but some of the theories are, as far as priorities, there are structures that have overburden over them, where there's hydrates on the ocean floor that have some actual silt and mud and rock over top. And that offers an opportunity to control the pressures a little bit more, because you've got some sort of a cap rock system. But if they're just free and open on the ocean floor, that's a difficult prospect. And I don't know the ratio of how much is of one or the other kind. Okay.
Well, hello.
Hello.
Several of the presentations yesterday implied that technological advancements may still be insufficient in the future to expand the volume of energy resources available to global demand. Would you happen to take a more optimistic view of technology's influence on energy resources for the future?
Yeah, absolutely. I think you can take a position, and people do. I like to be optimistic. I like to think that if there's a challenge, if there's an issue, the free market's going to rally behind. They're going to put their money where they're going to need it. Okay, so if it's a question of, do I shut down? Do I change the way I live? Is it going to be caveman days again? We're going to do everything we can to see that it's not. And if that's trying to develop a technology for hydrates or photovoltaics, or there are a number of things too that can help us get to a sustainable energy system. There is nuclear. It's not the answer. Uranium's a finite resource, and it takes time to, even if you say, okay, you take away all of the problems with regulating and licensing and getting all that stuff, all the red tape out of the way, it still takes time to build them and get them up to speed. So I think just, there are lag times with certain technologies. Even you talk Alaska, if you want to drill anything in Alaska, there's a 7-year time lag. It's just, from the time that you site something to the time that you're getting actual production down here where we can use it. And again, the refineries might be an issue with that if the type of oil is such that the refineries aren't matching or have that capability to refine that specific oil. you might find yourself, you've got crude oil and no means to make the product that you need. So all these things really needed to be addressed, but I feel confident that nothing's going to happen so imminently that it's going to cause a big problem. There are advances being made all the time, every day, in all these different fields. Good time for one more or no? Real quick.
One of your graphs that you showed had a peak point.
Right.
And I wanted to know, you had said that this was just, I think it was Hubbard or
Yeah.
cycle. Was this something that, or was that something that you personally agreed with, or what is your position as far as our point of peak, or where we're going to, just reach our ultimate peak of oil production? And also, I just wanted to say, or add to that, Mr. Newman yesterday from ExxonMobil, I don't know if you heard that
I did not.
speech, but he said technology is the answer, and that with where we're at with technology right now, with our current reserves and some of the crude oil up in Canada, technology can actually stretch that up to 2030. So I just wanted to know what you think.
I think that I agree in great degree with Professor Economides, who wrote a book called Color of Oil, and he believes, and he lays the foundation for it, that there's a couple hundred more years of oil production out there, and it's there, and it's for that period of time, because the technology is going to be, as he said, the technology will help stretch that out. As far as the curve, the curve is simplistic. It just shows a nice little bell curve. If you show production in real terms over that time, you'll see that the curve is being pushed forward, and I think in large part to technology, being able to find new resources and extract from resources they couldn't have done in years past. So I think there's a finite amount of oil and gas. However, we're continually putting off that peak. How long can we do that? That's anybody's guess, and there's, again, a lot of fields of thought on that. Thank you very much.
Thank you, Brian. We have some more food for you out in another break. If you have any questions for Mr. Gann, he's, I'm sure, more than happy to talk to you about the technical details. But then I look forward to having you back in about 15 minutes for our next panel. Thank you.